Tonight, we're going to discover something that will fundamentally shift how you see yourself and the world beneath your feet. We're going to explore the true scale of Earth, not just how it compares to other planets or stars, but what it actually means to live on a world this size. Because here's something most people never think about. The ground you're standing on right now, this solid Earth that feels so permanent and massive, is actually a thin shell of rock floating on a sea of molten metal, wrapped in the thinnest imaginable layer of breathable air, hurtling through an emptiness so profound that the word empty doesn't begin to describe it. By the end of this journey, you're going to understand Earth in a way you never have before. You're going to see just how compact, how delicate, and how extraordinary this planet truly is. Before we dive in, if you enjoy these deep explorations of our place in the cosmos, a quick like or subscribe really helps this channel grow. It's a small gesture, but it makes a real difference. Now, let's begin. I want to start with something simple. Look at your hand. The skin covering your palm is about 1 to 2 millimeters thick in most places. That thin layer protects everything underneath. Your muscles, your blood vessels, your nerves. Without that skin, you'd be vulnerable to every germ, every temperature change, every sharp edge in the world. Your skin is what separates you from everything that could harm you. Now, here's something remarkable. Earth has skin too. We call it the crust. And relative to the size of our planet, Earth's crust is thinner than your skin relative to the size of your body. If Earth were the size of an apple, the crust would be thinner than the apple's peel. All of human civilization, every building, every mine, every tunnel we've ever dug, exists within this impossibly thin layer. The deepest humans have ever drilled into Earth is about 7.5 miles at the Kola Super Deep borehole in Russia. That project took over 20 years and they barely scratched the surface. Earth's radius is about 3,959 miles. That 7.5-mile borehole represents only about 0.19% of the distance to Earth's center. We've never come close to penetrating through our planet's skin. Beneath that thin crust lies the mantle, a layer of rock so hot it flows like extremely thick liquid over millions of years. The mantle extends down about 1,800 miles. Below that is the outer core, made of liquid iron and nickel, churning and flowing, generating Earth's magnetic field. And at the very center sits the inner core, a solid ball of iron about the size of the moon, compressed by the weight of everything above it into a dense metallic sphere with temperatures rivaling the surface of our star. But we can't reach any of that. We're confined to the surface, to this thin rocky shell that represents less than 1% of Earth's volume. Think about that. All of human existence, everything we've ever built or explored, occupies less than 1% of our own planet by volume. We haven't even fully explored our own world, and yet that world is incomprehensibly modest in the larger scheme of things. Let's talk about the atmosphere, because this is where Earth's delicate nature becomes truly apparent. The atmosphere is the blanket of air that surrounds our planet, allowing us to breathe, protecting us from radiation, and regulating our temperature. Without it, Earth would be a lifeless rock, like the moon. How thick is this atmosphere? Well, there's no hard boundary where air ends and space begins. The atmosphere just gets thinner and thinner as you go higher. But most of the air, about 99% of it, exists within the first 20 miles above Earth's surface. The part we can actually breathe, the troposphere, extends about 11 to 12 miles up at the equator, though it's considerably thinner at the poles, dropping to around 4 or 5 miles. 11 to 12 miles. That's it. If you drove straight up at highway speed, you'd run out of breathable air in about 11 or 12 minutes. The entire life-supporting atmosphere, the air that every human, animal, and plant depends on, could be crossed in a short drive. Here's a way to visualize this. If Earth were a globe sitting on your desk, about 12 inches in diameter, the atmosphere would be thinner than a coat of varnish on that globe's surface. You couldn't even see it. It would be less than the thickness of a piece of paper. That invisible film is everything that stands between life on Earth and the deadly vacuum of space. The astronauts who have seen Earth from orbit all describe the same thing. They're struck by how thin the atmosphere looks. From space, you can see it as a faint blue line hugging the curve of the planet. They describe feeling suddenly protective of Earth, realizing how vulnerable that thin blue line really is. This is called the overview effect, and nearly every astronaut experiences it. Let's put some numbers on Earth's size to really understand what we're dealing with. Earth has a diameter of about 7,918 miles at the equator. It's actually slightly wider at the equator than from pole to pole because the spinning motion causes a slight bulge. The difference is only about 27 miles. Not much in absolute terms, but enough to make Earth technically an oblate spheroid rather than a perfect sphere. The circumference at the equator, the distance around Earth's middle, is about 24,901 miles. If you could walk that distance at a steady 3 miles per hour, walking 8 hours a day, it would take you about 2 years and 10 months. Ferdinand Magellan's expedition, the first to circumnavigate the globe, took nearly 3 years, sailing from 1519 to 1522. Most of the crew, including Magellan himself, died along the way. Today, a commercial jet can circle the Earth in about 45 hours of flight time. The International Space Station does it in about 90 minutes, orbiting at roughly 17,500 miles per hour. But even at those speeds, the journey takes measurable time. Earth is genuinely large from a human perspective. The surface area of Earth is about 197 million square miles. 71% of that is water, leaving only about 57 million square miles of land. And not all of that land is habitable. Deserts, mountains, ice caps, and other extreme environments make large portions of Earth's land surface challenging or impossible for permanent human settlement. The total habitable land area, the places where humans could reasonably live year-round, is estimated at about 24 million square miles. That's only about 12% of Earth's total surface. We think of Earth as our planet, but really, we occupy only a modest fraction of it. Now let's start making some comparisons. Because Earth's size only makes sense when you compare it to other things. The Moon is about 2,159 miles in diameter. That's roughly 27% of Earth's diameter, or about 1/4. If Earth were a basketball, the Moon would be a tennis ball. The Moon's surface area is about 14.6 million square miles, which is actually smaller than the continent of Asia. The distance to the Moon is about 238,900 miles on average. This varies because the Moon's orbit is elliptical, ranging from about 225,000 miles at its closest to about 252,000 miles at its farthest. Here's something most people don't realize. You could fit all the other planets in our solar system in the gap between Earth and the Moon with room to spare. Let me repeat that because it's worth emphasizing. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune could all be lined up in a row between Earth and the Moon. Their combined diameters add up to about 233,000 miles, leaving several thousand miles to spare. That's how far away the Moon really is, and it's our closest celestial neighbor. When you look at the Moon in the night sky, it appears about the same size as our star does during the day. This is a remarkable coincidence. Our star is about 400 times larger than the Moon, but it's also about 400 times farther away. This cosmic accident is why we get total solar eclipses, where the Moon perfectly covers the solar disk. In a few 100 million years, as the Moon continues drifting away from Earth, total eclipses will no longer be possible. We happen to live at the right time to witness them. Let's talk about our star, because this is where Earth starts to seem quite modest indeed. The star, at the center of our solar system, has a diameter of about 864,000 miles. If you lined up Earths across that diameter, you'd need about 109 of them. But diameter only tells part of the story. Volume is what really matters, and volume increases with the cube of the diameter. Our central star could contain about 1,300,000 Earths by volume. Let that sink in. Everything on Earth, every mountain, every ocean, every city, every person who has ever lived, all of it exists on a planet that could fit inside our star over 1 million times. The mass is even more impressive. Our star contains about 99.86% of all the mass in the entire solar system. Everything else combined, all 8 planets, all the moons, all the asteroids, all the comets, all the dust and debris, makes up only 0.14%. Our star dominates the solar system so completely that everything else is essentially a rounding error. And yet, by stellar standards, our star is completely ordinary. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's middle-aged at about 4.6 billion years old, roughly halfway through its expected lifespan. It's not particularly large, not particularly bright, not particularly hot. It's just an average star, one of hundreds of billions in our galaxy alone. The distance from Earth to our star is about 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. So when you look at the sky during the day, you're seeing our star as it was over 8 minutes ago. If something dramatic happened to it right now, we wouldn't know for over 8 minutes because the information can only travel at the speed of light. Let me give you some travel time comparisons to make this distance feel real. If you could drive to our star at highway speed, 60 miles per hour, never stopping, it would take you about 177 years. A commercial jet at 550 miles per hour would take about 19 years. Even the fastest spacecraft ever built, the Parker Solar Probe, which reaches speeds over 400,000 miles per hour at its closest approach, takes months to complete its journey. Now let's look at the other planets in our solar system, because Earth's place among them is instructive. Mercury is the smallest planet, with a diameter of about 3,032 miles, roughly 38% of Earth's diameter. Mercury is so compact that you could fit about 18 Mercuries inside Earth by volume. It orbits very close to our star, completing a year in just 88 Earth days. But because it rotates so slowly, one day on Mercury, from sunrise to sunrise, lasts about 176 Earth days. A day is longer than a year. Venus is almost Earth's twin in size, with a diameter of about 7,521 miles, 95% of Earth's. The two planets have similar mass and similar surface gravity, but that's where the similarities end. Venus has a thick atmosphere of carbon dioxide that creates a runaway greenhouse effect. Surface temperatures reach about 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 90 times higher than Earth's, equivalent to being half a mile underwater in our oceans. Venus shows us what could happen to an Earth-sized planet if conditions go wrong. It's a cautionary example of runaway climate change. Venus might have had liquid water oceans in the distant past, but today it's a hellscape where the atmosphere itself would crush and poison you before the heat could kill you. Mars is smaller than Earth, with a diameter of about 4,212 miles, roughly 53% of Earth's. You could fit about 6 Mars planets inside Earth by volume. Mars is often called Earth's sister planet because it's the most Earth-like world in our solar system. It has polar ice caps, seasons, and evidence of ancient water. But Mars lost most of its atmosphere billions of years ago, probably because it lost its magnetic field. Without a strong magnetic field, the solar wind, that stream of charged particles flowing outward from our star, gradually stripped away Mars's atmosphere. Without a thick atmosphere, liquid water couldn't exist on the surface. It either froze or evaporated into space. Today, Mars is a cold, dry desert with an atmospheric pressure less than 1% of Earth's. Beyond Mars lies the asteroid belt, a region containing millions of rocky fragments that never coalesced into a planet. The largest object there, Ceres, has a diameter of only about 588 miles. You could fit more than 13 Ceres objects across Earth's diameter. Despite containing millions of objects, the asteroid belt is mostly empty space. If you flew through it, you'd likely never see an asteroid with your naked eyes because the distances between them are so immense. Then we reach the giants. Jupiter dominates the outer solar system like nothing else. With a diameter of about 86,881 miles, Jupiter is about 11 times wider than Earth, but volume increases cubically. So Jupiter could contain about 1,321 Earths inside it. Jupiter is so massive that it contains more mass than all other planets combined, multiplied by 2.5. It has its own system of at least 95 moons, some larger than Mercury. The Great Red Spot, that famous storm in Jupiter's atmosphere, is itself larger than Earth. Earth could fit inside Jupiter's storm. Saturn, famous for its beautiful rings, has a diameter of about 72,367 miles, roughly 9 times Earth's diameter. By volume, Saturn could hold about 764 Earths. Saturn's density is remarkably low, lower than water. If you could find a bathtub big enough, Saturn would float in it. Saturn's rings are spectacular, extending outward for about 282,000 miles from the planet's center. But they're surprisingly thin, averaging only about 30 feet thick in most places. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. Uranus and Neptune are the ice giants of the outer solar system. Uranus has a diameter of about 31,518 miles, about 4 times Earth's diameter, and could contain about 63 Earths by volume. It's tilted completely on its side, with its axis of rotation nearly parallel to its orbital plane. Nobody knows exactly why, but it was probably knocked over by a collision with a large object early in its history. Neptune, the farthest planet, has a diameter of about 30,599 miles and could hold about 57 Earths. Neptune has the strongest winds in the solar system, reaching over 1,200 miles per hour At that distance from our star, Neptune takes about 165 Earth years to complete a single orbit. The planet was discovered in 1846, which means it has completed less than 2 full orbits since we first spotted it. Looking at this planetary lineup, you might think Earth is reasonably sized. After all, we're larger than Mercury, Mars, and Venus by various measures. We're the largest rocky planet in our solar system, but the gas giants dwarf us so completely that the comparison becomes almost absurd. Jupiter alone could swallow Earth over 1,000 times. And this is just our solar system. Beyond its edges, the scale increases by factors that become difficult to comprehend. The nearest star to our system is Proxima Centauri, a small red dwarf about 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at about 186,000 miles per second. That works out to roughly 5.88 trillion miles per light-year. So Proxima Centauri is about 25 trillion miles away. Let me try to make that distance meaningful. Remember how our central star is about 93 million miles from Earth. Proxima Centauri is about 268,000 times farther than that. If the distance from Earth to our star were represented by 1 inch, the distance to Proxima Centauri would be about 4 miles. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's been traveling for over 47 years and has covered about 15 billion miles. At that rate, it would still need roughly 73,000 years to reach Proxima Centauri. And it's not even heading in that direction. Even if we could build a spacecraft that traveled at 10% of light speed, which is far beyond our current capabilities, it would still take over 42 years to reach the nearest star. The distances between stars are genuinely, almost impossibly immense. And here's something crucial to understand. At these distances, Earth becomes invisible. If you were at Proxima Centauri looking back toward our solar system, you couldn't see Earth at all, not with any telescope we can currently imagine. Our star would appear as a bright point of light, and Earth would be lost in the glare, too compact and too close to its star to detect directly. The Milky Way galaxy, our cosmic home, contains somewhere between 200 billion and 400 billion stars. Our star is just one of them. Located about 26,000 light-years from the galactic center in a minor spiral arm called the Orion Spur. We're in the galactic suburbs, about 2/3 of the way out from the center, in a relatively quiet region where stars aren't packed too densely together. The Milky Way itself is about 100,000 light-years across. If you could somehow travel at light speed, which is impossible for anything with mass, it would still take you 100,000 years to cross from one side of our galaxy to the other. The last time our star was at its current position in galactic orbit, dinosaurs were just beginning to evolve on Earth. It takes about 225 million years for our solar system to complete one trip around the galactic center. At galactic scales, Earth doesn't just become compact, it becomes inconceivable. If you made a scale model of the Milky Way the size of the continental United States, our entire solar system would be smaller than a grain of sand. And Earth would be so much tinier than that grain of sand that no metaphor captures it accurately. But here's the thing. The Milky Way is just one galaxy among trillions in the observable universe. The nearest large galaxy is Andromeda, about 2.5 million light-years away. When you look at Andromeda in the night sky, you're seeing light that left that galaxy when our ancestors were just beginning to use stone tools. Andromeda contains about 1 trillion stars, more than twice as many as the Milky Way. The observable universe, the part we can theoretically see given the age of the universe and the speed of light, is about 93 billion light-years across. It contains an estimated 2 trillion galaxies, each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is somewhere around 200 sextillion. That's a 2 followed by 23 zeros. And Earth is one planet orbiting one of those stars. If you selected a random star from all the stars in the observable universe, your chances of picking our star would be 1 in 200 sextillion. And even if you somehow did pick our star, you'd then have to identify Earth among all the objects in our solar system. The probability of randomly selecting Earth from everything in the observable universe is so minuscule that the number is effectively 0. Now, I want to shift gears and talk about something different, because Earth's modest size isn't just about comparisons. It's also about understanding what makes our planet special, despite that modesty. Earth is, as far as we know, the only place in the universe where life exists. We might discover microbial life elsewhere, perhaps on Mars, or in the subsurface oceans of Europa or Enceladus. There might be intelligent civilizations scattered throughout the cosmos that we haven't detected yet. But right now, today, Earth is the only confirmed location of life in all the universe we can observe. This makes Earth extraordinary in a way that has nothing to do with size. A diamond is compact compared to a boulder, but we don't value boulders more than diamonds. What matters is what something is, not just how big it is. What makes Earth capable of supporting life? It's a combination of factors that might be extraordinarily rare in the universe. First, Earth is the right distance from our star. Too close and water would evaporate. Too far and it would freeze. Earth sits in what astronomers call the habitable zone, the Goldilocks region, where temperatures allow liquid water to exist on the surface. This seems simple, but the habitable zone is actually quite narrow. Venus is only about 28% closer to our star than Earth is, and it's a hellscape. Mars is about 52% farther, and it's a frozen desert. Second, Earth has the right mass. A planet needs enough mass to hold onto an atmosphere. If Earth was smaller, like Mars, it might have lost its atmosphere to space. If it were much larger, it might have accumulated a thick hydrogen-helium atmosphere like the gas giants, creating crushing pressures and no solid surface. Third, Earth has a magnetic field. This invisible shield is generated by the motion of liquid iron in Earth's outer core. It deflects the solar wind, that stream of charged particles constantly flowing outward from our star. Without this magnetic field, the solar wind would gradually strip away our atmosphere as it did to Mars. We'd lose our air, our water, and eventually our lives. The magnetic field extends far into space, creating a region called the magnetosphere that stretches hundreds of thousands of miles toward the night side of Earth. When charged particles from the solar wind do penetrate this shield, they spiral down along magnetic field lines toward the poles, colliding with atoms in the upper atmosphere. These collisions produce one of nature's most spectacular displays, the aurora. The northern lights and southern lights dance across polar skies in curtains of green, red, purple, and blue. Ancient peoples saw them as spirits of the dead, messages from gods, or omens of great events. We now understand them as visible evidence of the invisible shield protecting our planet, a beautiful reminder that Earth is constantly under bombardment from space and constantly defending itself. The magnetic field also helps many animals navigate. Birds, sea turtles, salmon, and even some bacteria can sense magnetic fields and use them to find their way across vast distances. Migratory birds travel thousands of miles using a magnetic map they can somehow perceive. How exactly they sense magnetism remains one of biology's intriguing mysteries. Earth's magnetic field isn't static. It wanders, weakens, and occasionally flips entirely, with the north and south magnetic poles trading places. These reversals have happened hundreds of times over Earth's history. Most recently, about 780,000 years ago. During a reversal, the field weakens dramatically, potentially exposing the surface to more radiation. Life has survived every reversal so far, but we don't fully understand the consequences. Fourth, Earth has plate tectonics. The slow movement of crustal plates creates mountains, causes earthquakes, and drives the carbon cycle. Volcanic eruptions release carbon dioxide into the atmosphere, while weathering of rocks removes it. This creates a natural thermostat that has helped regulate Earth's temperature over billions of years. Most rocky planets don't have active plate tectonics. We're unusual in this regard. Fifth, Earth has a large moon. The moon stabilizes Earth's axial tilt, preventing wild swings that would cause extreme climate variations. Without the moon, Earth's axis might wobble chaotically over millions of years, making the development of complex life much more difficult. The moon also creates tides, which might have played a role in the origin of life by creating tidal pools, where chemicals could concentrate and react. Sixth, Earth has liquid water. Water is essential for life as we know it. It's the solvent in which biochemistry happens. Earth has enormous oceans covering 71% of its surface, plus lakes, rivers, ice caps, and groundwater. The total amount of water on Earth is about 326 million trillion gallons. Each of these factors is important on its own. Together, they create a world uniquely suited for life. Change any one of them significantly, and Earth might be as lifeless as Mars or Venus. How rare is this combination? We don't know. We've discovered thousands of exoplanets orbiting other stars, some in habitable zones, some roughly Earth-sized. But we can't yet determine if any of them have magnetic fields, plate tectonics, large moons, or liquid water. We can't yet detect the chemical signatures of life in their atmospheres. Some scientists think Earth-like planets might be common, and life might be widespread throughout the universe. Others think the conditions for life are so specific, so dependent on unlikely coincidences, that Earth might be extraordinarily rare, perhaps even unique. Until we find evidence otherwise, we have to treat Earth as something to be protected. We have to recognize that everything we know about life, every organism from bacteria to blue whales, every ecosystem from tropical rainforests to deep ocean vents, all of it exists on this one world. There is no backup Earth. There is no planet B waiting for us if we make this one uninhabitable. Let's talk about Earth's atmosphere in more detail, because this is one of the most remarkable things about our planet. The atmosphere is about 78% nitrogen, 21% oxygen, and about 1% everything else, including argon, carbon dioxide, and trace gases. This specific mixture is unusual. Most rocky planets have atmospheres dominated by carbon dioxide, like Venus and Mars. Earth's oxygen-rich atmosphere is a direct result of life. For the first 2 billion years of Earth's history, there was essentially no free oxygen in the atmosphere. Early Earth's air was probably a mixture of nitrogen, carbon dioxide, methane, and water vapor. Then, sometime around 2.4 billion years ago, something remarkable happened. Cyanobacteria, simple photosynthetic organisms, evolved the ability to split water molecules and release oxygen as a waste product. At first, This oxygen was absorbed by iron in the oceans and rocks, but eventually, after hundreds of millions of years, the oxygen accumulated faster than it could be absorbed. Levels began to rise. This was catastrophic for most life at the time, because oxygen is actually toxic to organisms that hadn't evolved to use it. The Great Oxygenation Event, as it's called, was probably the first mass extinction in Earth's history. But some organisms adapted. They evolved to not just tolerate oxygen, but to use it, extracting energy from food through aerobic respiration, which is far more efficient than the anaerobic processes that came before. This adaptation eventually led to all complex life on Earth, including us. The oxygen in the air you're breathing right now was produced by life. Without photosynthetic organisms, mostly plants and cyanobacteria, Earth's atmosphere would have very little free oxygen. And without oxygen, you couldn't survive. Every breath you take is a gift from billions of years of photosynthesis. Here's something to contemplate about Earth's energy balance. Our planet receives about 174 petawatts of solar energy at the top of the atmosphere. About 30% of that is reflected back into space by clouds, ice, and other reflective surfaces. The rest is absorbed, warming the land, the oceans, and the atmosphere. This incoming energy must be balanced by outgoing energy, or Earth's temperature would change. And it does balance remarkably well. Earth radiates infrared energy back into space. And over time, the outgoing energy matches the incoming energy. This is why Earth's temperature has remained relatively stable for billions of years, despite the star gradually brightening. The greenhouse effect is part of this balance. Without greenhouse gases, Earth would radiate heat away too efficiently and freeze. With too many greenhouse gases, it retains too much heat and warms. For most of Earth's history, natural processes have maintained this balance within limits that allow life to flourish. The atmosphere also contains carbon dioxide, which plays a crucial role in regulating Earth's temperature. Carbon dioxide is a greenhouse gas, meaning it traps heat in the atmosphere. Without any greenhouse gases, Earth's average temperature would be about 0 degrees Fahrenheit, well below freezing. With too much, Earth would overheat like Venus. For most of Earth's history, natural processes have kept carbon dioxide at levels that maintained comfortable temperatures. Volcanoes release carbon dioxide, weathering of rocks absorbs it, and the balance has fluctuated within livable ranges. But human activities, primarily burning fossil fuels, have been adding carbon dioxide to the atmosphere faster than natural processes can remove it. Atmospheric carbon dioxide levels are now higher than they've been in at least 800,000 years, probably several million years. This matters because even modest changes in atmospheric composition can have large effects on climate. The difference between an ice age and a warm period can be as little as a few degrees in global average temperature. We're currently on track to add several degrees more within the next century if we don't change course. I mention this not to be political, but to emphasize how sensitive our planet is to change. The thin atmosphere that makes life possible responds to perturbations. We're conducting an uncontrolled experiment on the only planet we have, and we don't know exactly how it will turn out. Let's think about water. Because water is central to understanding Earth's uniqueness. Earth is sometimes called the blue planet because of how much water covers its surface. Seen from space, the dominant color is blue, the color of our oceans. The Pacific Ocean alone covers more area than all the land on Earth combined. But here's something surprising. Despite all that water, the total amount is actually quite modest relative to Earth's size. If you collected all the water on Earth, all the oceans, lakes, rivers, ice caps, groundwater, and atmospheric water vapor, and formed it into a sphere, that sphere would be only about 860 miles in diameter. That's it. All the water on Earth would fit in a sphere smaller than the distance from New York to Chicago. Put that sphere next to Earth, and it would look like a marble next to a basketball. We think of Earth as a water world, but really it's a rock world with a thin film of water on its surface, and most of that water is ocean water, which is too salty for humans to drink. Only about 2.5% of Earth's water is fresh water, and most of that fresh water is locked up in ice caps and glaciers, or deep underground. The water in rivers and lakes, the easily accessible fresh water that humans depend on, represents only about 1% of Earth's total water. Think about that. All the rivers and lakes on Earth, all the easily accessible drinking water for 8 billion people, represents less than 1/100% of our planet's total water. We take water for granted, turning on taps and expecting it to flow, but fresh water is actually a limited resource. Here's something remarkable about our oceans. Despite covering 71% of Earth's surface, we've explored only about 5% of them. The deep ocean remains more mysterious than the surface of Mars. We have better maps of the moon than we do of our own ocean floor. The deepest point in the ocean, the Challenger Deep in the Mariana Trench, reaches down about 36,000 feet, nearly 7 miles below sea level. More people have walked on the moon than have visited the bottom of the Mariana Trench. The pressure at that depth is over 1,000 times atmospheric pressure, enough to crush most submarines. Yet life exists even there. Strange creatures have adapted to the crushing pressure, the eternal darkness, and the near-freezing temperatures. Ghostly fish with translucent bodies drift through the abyss. Giant amphipods scavenge whatever organic matter drifts down from above. Life finds a way, even in the most extreme environments our planet offers. The ocean's average depth is about 12,100 feet, more than 2 miles. If you could drain the oceans, you'd reveal a landscape more dramatic than anything on land. Mountain ranges taller than the Himalayas, canyons deeper than the Grand Canyon, vast plains of sediment stretching for thousands of miles, the mid-ocean ridges where tectonic plates pull apart and new crust forms, constitute the longest mountain chain on Earth, winding over 40,000 miles around the globe like the seam on a baseball. Hydrothermal vents along these ridges create oases of life in the deep desert of the ocean floor. Superheated water, sometimes exceeding 700 degrees Fahrenheit, gushes from the seafloor, rich in minerals and chemicals. Despite temperatures that would kill most organisms, specialized bacteria thrive here, forming the base of food chains that support tube worms, giant clams, and strange eyeless shrimp. These ecosystems don't depend on sunlight at all. They run on chemical energy from Earth's interior, a form of life we didn't know existed until 1977. This makes us wonder. If life can exist in such alien conditions on our own planet, where else might it be hiding? What strange ecosystems might we find on the ocean floor of Europa, Jupiter's ice-covered moon? What might lurk in the subsurface oceans of Enceladus? Let's shift to thinking about life on Earth, because this is another way to understand our planet's scale and uniqueness. Scientists estimate that there are roughly 8.7 million species on Earth, though this number is uncertain because most species haven't been discovered and catalogued yet. Of those, about 2.2 million have been formally described and named. Every year, scientists discover thousands of new species, mostly insects, plants, and microorganisms. But here's something remarkable. All life on Earth, every species from bacteria to humans, shares a common ancestor. All of us use the same genetic code, the same basic biochemistry. We're all related. You share about 50% of your DNA with a banana and about 99% with a chimpanzee. This suggests that life arose on Earth only once, as far as the evidence indicates. About 3.8 billion years ago, something happened in Earth's ancient oceans. Non-living chemicals organized themselves into something that could reproduce and evolve. That original life form, whatever it was, gave rise to everything alive today. We don't know how life originated. It's one of the biggest unsolved questions in science. We can recreate some of the conditions of early Earth in laboratories and produce complex organic molecules, but we haven't been able to create life from scratch. The gap between non-living chemistry and living systems remains mysterious. Some scientists think life arises easily wherever conditions are right. In this view, life might be common throughout the universe. Others think the origin of life required such an unlikely series of events that it might have happened only once here on Earth. We simply don't know. What we do know is that once life got started, it evolved into incredible diversity. From those simple beginnings 3.8 billion years ago, life has produced everything from deep-sea tube worms that live in complete darkness near volcanic vents, to birds that migrate thousands of miles every year, to organisms that can survive in boiling water, freezing ice, and even the vacuum of space. Life has transformed Earth. The oxygen in our atmosphere was produced by life. The limestone cliffs of Dover are made of the shells of tiny marine organisms. The coal and oil we burn are the remains of ancient plants and animals. Life has shaped the planet in profound ways. And among all that life, one species developed the ability to understand its place in the universe. Humans appeared only about 300,000 years ago, a blink of an eye in geological terms. We developed language, tools, agriculture, writing, science. We built telescopes that could see galaxies billions of light years away. We sent robots to Mars and probes to the outer planets. We discovered the age of the universe and the structure of atoms. This is remarkable. We are stardust that has become conscious, matter that has organized itself into beings capable of comprehending the cosmos. As far as we know, this has happened only once, only here, only on this world. Let me tell you about the pale blue dot. In 1990, the Voyager 1 spacecraft was about 3.7 billion miles from Earth, heading out of the solar system. The astronomer Carl Sagan persuaded NASA to turn the spacecraft's cameras back toward Earth for one final photograph. The resulting image shows Earth as a tiny pale blue dot, less than a single pixel in size, suspended in a beam of scattered sunlight. This is what our planet looks like from the edge of the solar system. Sagan wrote eloquently about this image. He pointed out that everyone who ever lived, every king and peasant, every hero and coward, every creator and destroyer of civilization lived out their lives on that tiny dot. Every war ever fought, every love story, every moment of joy and tragedy happened there. The pale blue dot reminds us of our scale. It shows us that from even a modest cosmic distance, Earth essentially disappears. But it also reminds us of our uniqueness. That pale blue dot is, as far as we know, the only place where life exists, where consciousness has emerged, where beings can wonder about their place in the cosmos. Earth is compact, yes. But Earth is also home. It's the only home we've ever known. Now let's talk about time, because understanding Earth's age gives us another perspective on our place in the scheme of things. Earth formed about 4.54 billion years ago from the same cloud of gas and dust that formed our star and the rest of the solar system. The early Earth was nothing like the world we know today. It was a molten ball, constantly bombarded by asteroids and comets. The impacts were so intense that the surface remained liquid for hundreds of millions of years. Gradually, Earth cooled. A solid crust formed. The intense bombardment slowed. Water, probably delivered by comets and asteroids, accumulated on the surface to form oceans. Somewhere in those ancient seas, life arose. For most of Earth's history, life was simple. Single-celled organisms dominated for about 3 billion years. Complex multicellular life didn't appear until about 600 million years ago. The famous Cambrian explosion, when most major animal groups first appeared in the fossil record, happened about 540 million years ago. Dinosaurs appeared about 230 million years ago and dominated Earth for over 160 million years. They went extinct 66 million years ago, when an asteroid about 6 miles across struck what is now Mexico's Yucatan Peninsula. The impact triggered massive tsunamis, global wildfires, and a nuclear winter that blocked sunlight for years. About 75% of all species went extinct. Mammals, which had been compact marginal creatures during the age of dinosaurs, suddenly had the opportunity to diversify. They filled the ecological niches left empty by the dinosaurs' extinction. Primates appeared about 65 million years ago. The first members of our genus, Homo, appeared about 2 million years ago. Anatomically modern humans, Homo sapiens, appeared only about 300,000 years ago. Let me put this timeline in perspective. If Earth's entire history were compressed into a single year, with January 1st being Earth's formation and December 31st being today, life would appear in late March. Complex multicellular life wouldn't appear until mid-November. Dinosaurs would dominate from December 13th until December 26th. Humans would appear at about 11:59 p.m. on December 31st. All of recorded human history, everything from the first writing to the present day, would happen in the last 13 seconds of the year. We are newcomers. Earth existed for 4 billion years before humans appeared. The dinosaurs ruled for over 160 million years. We've been around for 300,000 years, and civilized for about 10,000. On geological timescales, we just got here, and Earth will continue long after we're gone. Our star has about 5 billion years of fuel left. Eventually, it will expand into a red giant, possibly engulfing Earth. But that's billions of years away. The more immediate question is whether human civilization will persist for thousands or millions of years, or whether we'll be a brief flash in Earth's long history, gone as quickly as we appeared. Let's think about what the future might hold. In the short term, the next few thousand years, Earth will remain much as it is, assuming we don't cause catastrophic changes ourselves. The continents will continue drifting slowly. The climate will change, both naturally and due to human activity. Species will evolve and go extinct. Life will continue. In the medium term, millions of years, larger changes will occur. The continents will reconfigure. Africa is colliding with Europe, eventually closing the Mediterranean Sea. Australia is moving towards Southeast Asia. In about 250 million years, a new supercontinent will form. We've seen this before. as Earth has gone through cycles of supercontinent formation and breakup throughout its history. In the long term, billions of years, more dramatic changes await. Our star is gradually getting brighter as it ages. In about 1 billion years, it will be bright enough to make Earth's oceans begin evaporating. The planet will become increasingly inhospitable. Eventually, perhaps in about 4 billion years, our star will exhaust its hydrogen fuel and expand into a red giant. Earth might survive on the outer edges of the expanded star, but it will be a scorched, lifeless world. Eventually, our star will shed its outer layers and become a white dwarf, a tiny, dense remnant that will slowly cool over trillions of years. Earth, if it survives, will orbit a dim, cold ember, receiving almost no light or heat. The solar system will be dark and cold, but that's far in the future. For now, Earth is warm and alive, the only such world we know of in all the universe. Let's talk about earthquakes and volcanoes, because these phenomena reveal something profound about the thin shell of rock we live on. Earth's crust is broken into about 15 major tectonic plates and several smaller ones. These plates float on the hot, flowing mantle beneath them, moving at speeds of a few inches per year. Where plates collide, one often gets pushed beneath the other in a process called subduction. Where they pull apart, new crust forms from magma welling up from below. Where they slide past each other, friction builds up and is released as earthquakes. The ring of fire around the Pacific Ocean marks the boundaries of several major plates. About 90% of all earthquakes occur along this ring. The most powerful earthquakes can release energy equivalent to thousands of nuclear bombs. The 2011 earthquake off Japan's coast released energy equivalent to about 475 million tons of TNT, causing a massive tsunami that killed nearly 20,000 people. We build our cities and our lives on a surface that's constantly moving and occasionally shaking violently. The solid ground beneath your feet isn't as solid as it seems. It's just the cooled skin on a planet that's still hot and active inside. Volcanoes remind us of this even more dramatically. There are about 1,500 potentially active volcanoes on Earth's surface, and, on average, about 50 to 70 erupt each year. Most eruptions are relatively modest, but some are catastrophic. The Tambora eruption in 1815 was the most powerful in recorded history. It ejected so much ash and sulfur dioxide into the atmosphere that 1816 became known as the year without a summer. Crops failed across the northern hemisphere. Tens of thousands died from famine and disease. And that was a relatively normal volcanic eruption in geological terms. Supervolcanoes are even more terrifying. Yellowstone National Park sits atop a volcanic hotspot that has produced several massive eruptions over the past few million years. The most recent major eruption, about 640,000 years ago, ejected over 240 cubic miles of material into the atmosphere. If a similar eruption happened today, it would likely cause a volcanic winter lasting years, devastate agriculture worldwide, and potentially threaten human civilization. We don't think about these risks in our daily lives. The odds of a supervolcanic eruption in any given year are extremely low. But over geological time, these events are not just possible, but inevitable. Earth has experienced them before and will experience them again. We live on a geologically active planet, and that activity can be deadly. Let me tell you about mass extinctions, because they show how precarious life on Earth can be. Scientists have identified 5 major mass extinctions in Earth's history. events where a large percentage of all species went extinct in a relatively short period. The largest was the Permian-Triassic extinction, about 252 million years ago. An estimated 90 to 96% of all marine species and 70% of terrestrial vertebrate species went extinct. The cause is still debated, but probably involved massive volcanic eruptions in what is now Siberia, which released enormous amounts of carbon dioxide and methane, causing rapid climate change, ocean acidification, and possibly ocean anoxia, where the oceans lost their oxygen. Life nearly ended. The survivors were compact, often burrowing animals that could tolerate harsh conditions. Recovery took millions of years. This is sometimes called the Great Dying. The most famous mass extinction is the Cretaceous-Paleogene extinction about 66 million years ago, which killed the dinosaurs. An asteroid, about 6 miles across, struck what is now Mexico's Yucatan Peninsula, creating a crater over 110 miles wide. The impact ejected billions of tons of rock into the atmosphere, triggered global wildfires, and caused a years-long winter as dust and soot blocked sunlight. About 75% of all species went extinct, including all non-avian dinosaurs. The survivors included mammals, birds, reptiles, and marine life that could survive on detritus or stored food. From those survivors, modern life evolved. Here's what's sobering. Both of these mass extinctions happened because of relatively normal cosmic or geological events. Asteroid impacts happen regularly over geological time. Massive volcanic eruptions happen periodically. Earth has experienced 5 major mass extinctions and numerous smaller ones. There's no reason to think we're immune from future catastrophic events. In fact, some scientists argue we're currently in the 6th mass extinction, this one caused not by asteroids or volcanoes, but by us. Human activity has accelerated species extinctions to rates hundreds or thousands of times higher than the normal background rate. Habitat destruction, pollution, climate change, and overexploitation are driving species extinct at an alarming pace. This matters because biodiversity is what makes ecosystems resilient. The more species in an ecosystem, the better it can absorb shocks and continue functioning. As species disappear, ecosystems become more vulnerable, more prone to collapse. We're unraveling the web of life that sustains us. Let me talk about asteroid impacts in more detail, because this is one of the ways Earth's position in the cosmic shooting gallery becomes relevant to our survival. Space is full of rocks. Millions of asteroids orbit in our solar system, mostly in the asteroid belt between Mars and Jupiter. But some have orbits that cross Earth's path. These near-Earth objects range in size from small pebbles to objects miles across. Minor impacts happen all the time. Every day, Earth is struck by about 100 tons of dust and small meteoroids. Most burn up in the atmosphere as shooting stars. Occasionally, a larger object makes it through and hits the ground, creating a crater. Larger impacts are rarer but more devastating. The Tunguska event in 1908 involved an object probably 50 to 60 meters across that exploded in the atmosphere over Siberia. The blast flattened 800 square miles of forest. If it had happened over a city, millions would have died. The Chelyabinsk event in 2013 involved an object about 20 meters across that exploded over Russia. The blast injured about 1,500 people, mostly from broken glass. Videos of the fireball went viral, reminding us that cosmic impacts aren't just ancient history. Larger impacts are less frequent but more catastrophic. An object 100 meters across could destroy a city. An object 1 kilometer across could trigger global climate effects and kill millions or billions. An object 10 kilometers across, like the one that killed the dinosaurs, could end civilization and possibly drive humanity extinct. How often do these happen? Objects 100 meters across hit Earth about every few thousand years. Objects 1 kilometer across hit about every 500,000 years, on average. Extinction-level impacts happen roughly every 100 million years. The odds of being killed by an asteroid impact are actually comparable to the odds of dying in a plane crash, because while impacts are rare, they can kill huge numbers of people when they do occur. We've begun tracking near-Earth objects and could potentially deflect one if we had enough warning. But we haven't yet built the systems to do this reliably. This is another way Earth's position matters. We're a target in a cosmic shooting gallery. Most asteroids miss us, but over long enough time spans, impacts are inevitable. If humanity wants to survive for millions of years, we need to either prevent impacts or spread to multiple worlds so that no single impact can wipe us out. Let me discuss something called the Goldilocks principle, because it helps explain why Earth is so special. Earth exists in a narrow range of conditions that allow liquid water to exist on the surface. Too close to our central star, and water would evaporate, as it did on Venus. Too far, and it would freeze, as it has on Mars. We're at just the right distance, not too hot and not too cold. But distance from our star isn't the only factor. Earth also has the right atmospheric pressure. Liquid water can only exist if atmospheric pressure is high enough. On Mars, even though temperatures sometimes rise above freezing, the atmospheric pressure is so low that water sublimates directly from ice to vapor without passing through a liquid phase. Earth also has the right atmospheric composition. If our atmosphere were mostly hydrogen, like the gas giants, water chemistry would be completely different. If it were mostly carbon dioxide, like Venus, runaway greenhouse warming would make the surface uninhabitable. Earth has the right rotation rate. A day is 24 hours long. If Earth rotated much slower, temperature extremes between day and night would be more severe. If it rotated much faster, weather patterns would be more violent. Earth has the right axial tilt. Our axis is tilted about 23.5 degrees relative to our orbital plane. This tilt gives us seasons, which distribute heat more evenly around the planet and drive weather patterns that circulate nutrients and water. If the tilt were much greater, seasonal extremes would be more severe. If it were much less, the equator would receive almost all the heat and the poles would be much colder. Seasons are more important than most people realize. They drive the rhythms of life on Earth, triggering animal migrations, plant flowering, insect emergencies, and countless other biological events. The changing length of days tells organisms when to reproduce, when to hibernate, when to migrate. Without seasons, the intricate timing that coordinates ecosystems might never have developed. Consider the Arctic tern, a bird that experiences more daylight than any other creature on Earth. It breeds in the Arctic summer, then flies to the Antarctic to experience another summer there, covering roughly 44,000 miles each year. Over its lifetime, an Arctic tern might fly the equivalent of 3 round trips to the moon. Seasons make this possible. Without the tilt that creates seasons, these epic migrations would have no purpose. Seasons also drive ocean circulation. As polar regions cool in winter, surface water becomes denser and sinks, creating deep currents that circulate nutrients and oxygen throughout the ocean depths. This thermohaline circulation acts like a global conveyor belt, connecting all the world's oceans and affecting climate on every continent. Without seasonal temperature variations, this circulation might weaken, with profound effects on marine ecosystems and weather patterns. The tilt that gives us seasons isn't stable on its own. Earth wobbles like a spinning top, and over tens of thousands of years, its tilt varies between about 22 and 24.5 degrees. These slow changes in tilt, combined with variations in Earth's orbital shape and the orientation of its axis, create the Milankovitch cycles that drive ice ages. We're currently in an interglacial period, one of the warmer phases between ice ages. The last ice age ended only about 12,000 years ago, when massive ice sheets covered much of North America and Europe. Human civilization arose entirely within this interglacial period. Agriculture, cities, writing, all of it developed in a climate that's been relatively stable and warm by geological standards. We don't know how civilization would fare if the climate shifted dramatically, either toward another ice age or toward temperatures warmer than anything humans have experienced. Earth has the right mass. Smaller planets can't hold on to atmospheres well. Larger planets might accumulate thick hydrogen-helium atmospheres that create crushing pressures. Earth is in the sweet spot, large enough to retain an atmosphere, but small enough to remain a rocky world with a solid surface. Gravity is worth dwelling on for a moment, because it shapes everything about our world. The surface gravity on Earth is about 9.8 meters per second squared. This number determines how high we can jump, how tall trees can grow, how our bodies are built. Our hearts pump blood against gravity. Our bones are strong enough to support our weight against gravity. Our entire biology is adapted to this specific gravitational pull. On a planet with stronger gravity, we'd need thicker bones, stronger muscles, and more powerful hearts. Animals would be shorter and stockier. Trees couldn't grow as tall. Walking would be more exhausting. On a planet with weaker gravity, the opposite would be true. We might be taller, more delicate, able to leap great distances. But weak gravity might also mean a thinner atmosphere, since gases would escape to space more easily. Gravity also keeps Earth's layers sorted. The heavy iron core sank to the center when Earth was young and molten. The lighter rocks floated upward to form the crust. Water, lighter still, pooled on the surface. Air, lightest of all, formed a thin layer on top. Gravity organized our planet into concentric shells, each with its own composition and properties. And gravity keeps the moon in orbit, the moon that stabilizes our axis and creates our tides. It keeps Earth in orbit around our star, at just the right distance for liquid water. It keeps our star from flying apart, balancing the outward pressure of fusion against the inward pull of its own mass. Gravity is the sculptor of the cosmos, and Earth exists because gravity shaped it just right. All of these factors had to come together for Earth to be habitable. Change any one of them significantly, and life might not be possible here. We don't know how common this combination is in the universe, but it might be quite rare. Let me tell you about some of the extreme conditions life has adapted to on Earth, because this tells us something about both the resilience of life and the range of environments our planet provides. Life on Earth exists in conditions that would kill most organisms. Extremophiles, as they're called, have adapted to environments we would consider utterly hostile. Thermophiles live in hot springs and hydrothermal vents where temperatures exceed 200 degrees Fahrenheit. The hottest environments where life has been found are around 250 degrees Fahrenheit, hot enough to sterilize most organisms. Yet these microbes thrive there. Psychrophiles, live in permanently frozen environments. Microbes have been found alive in Antarctic ice cores that are hundreds of thousands of years old. Some bacteria can metabolize at temperatures well below 0 degrees Fahrenheit by producing antifreeze proteins that prevent ice crystals from forming in their cells. Acidophiles live in extremely acidic environments. Some bacteria thrive in conditions with a pH below 1, more acidic than battery acid. They've been found in acid mine drainage, volcanic hot springs, and the stomachs of animals. Alkaliphiles live in extremely alkaline environments. Some bacteria thrive at pH levels above 11, caustic enough to dissolve organic matter. They've been found in soda lakes and industrial waste sites. Halophiles live in extremely salty environments. The Dead Sea, which is about 10 times saltier than the ocean, supports specialized microbes. Some halophiles can survive in saturated salt solutions. Barophiles live under extreme pressure. Microbes have been found at the bottom of the ocean where pressure exceeds 1,000 times atmospheric pressure. They've adapted their cell membranes and proteins to function under these crushing conditions. Radiophiles can survive extreme radiation. The bacterium Deinococcus radiodurans can survive radiation doses thousands of times higher than what would kill a human. It repairs its damaged DNA with remarkable efficiency. Some organisms combine multiple extreme tolerances. Tardigrades, also known as water bears, are microscopic animals that can survive freezing, boiling, extreme radiation, the vacuum of space, and pressures 6 times greater than the deepest ocean. They do this by entering a state called cryptobiosis, essentially shutting down their metabolism and waiting for conditions to improve. What does this tell us? Life is remarkably adaptable. Once it gets started, it can spread into almost any environment. But life also requires certain minimum conditions, liquid water chief among them. Without water, even extremophiles can't survive. This has implications for the search for life elsewhere. If life can survive such extreme conditions on Earth, perhaps it can survive in extreme environments on other worlds too. The subsurface oceans of Europa and Enceladus, the ancient lake beds of Mars, perhaps even the clouds of Venus, might harbor life. Let me share some scale comparisons that might help make Earth's size more intuitive. If Earth were shrunk to the size of a basketball, about 9.5 inches in diameter, here's what other things would be at the same scale. The Moon would be about the size of a tennis ball, orbiting about 24 feet away. Our central star would be about 90 feet in diameter, about the height of a 9-story building, located about 2 miles away. Jupiter would be about the size of a large beach ball, about 11 inches across, orbiting about 10 miles away. Neptune would be about the size of a baseball, orbiting about 57 miles away. The nearest star, Proxima Centauri, would be another building-sized sphere located about 526,000 miles away. That's more than twice the actual distance from Earth to the Moon. The nearest star, at basketball scale, would be farther than the actual Moon, and the Milky Way at this scale, it would be about 47 million billion miles across. That number is so large it's meaningless. Let me try a different approach. If the Milky Way was shrunk to the size of a dinner plate, about 12 inches across, our solar system would be smaller than a grain of sand, and Earth would be so much tinier than that grain of sand that no microscope could see it. If the observable universe was shrunk to the size of Earth, the Milky Way would be smaller than an atom. The solar system would be smaller than a proton. and Earth would be so infinitesimally minuscule that quantum mechanics would take over and it wouldn't have a defined size at all. These comparisons fail at some point because the scale differences are simply too large for human intuition to grasp. We evolved to understand distances from a few feet to a few miles. Anything larger than that, and our intuitions fail us. Here's another comparison that might help. If you could travel at highway speed, 60 miles per hour, non-stop, it would take you about 17 days to drive around Earth at the equator. It would take about 177 years to reach our central star. It would take about 48 million years to reach the nearest star. And it would take about 180 trillion years to reach the far side of the Milky Way. The universe is about 13.8 billion years old. Driving across the galaxy at highway speed would take more than 10,000 times longer than the universe has existed. Let me talk about what all of this means for the future of humanity. We're a young species. Modern humans have existed for about 300,000 years. Civilization, with agriculture and cities and writing, has existed for only about 10,000 years. Science and technology, as we know them, have existed for only a few hundred years. We've had the ability to travel to space for only about 65 years. In cosmic terms, we just appeared. The dinosaurs ruled Earth for 160 million years. If we lasted as long as the dinosaurs, we'd still have 159,700,000 years to go. That's about 53,000 times longer than recorded human history. What might we accomplish in that time? It's impossible to know, but let's speculate. In the near term, the next few centuries, we might establish permanent settlements on the Moon and Mars. These would be tenuous outposts at first, dependent on supplies from Earth. But over time, they might become self-sufficient. Humanity would become a multi-planetary species for the first. In the medium term, over thousands of years, we might spread throughout our solar system. Settlements on the moons of Jupiter and Saturn, mining operations in the asteroid belt, habitats in deep space, far from any planet. We might even begin transforming other worlds through terraforming, making them more Earth-like and habitable. In the long term, over millions of years, we might spread beyond our solar system. This would require technologies we don't yet have, probably some form of generation ship or suspended animation. Journeys to other stars would take decades or centuries, but over millions of years, we could populate thousands of star systems. In the very long term, over billions of years, we might spread throughout our galaxy and beyond. We might become a civilization spanning multiple galaxies. We might develop technologies so advanced that they seem like magic to us today. We might even engineer new stars or modify the fabric of space-time itself. Or we might fail. We might destroy ourselves through war or environmental collapse or runaway technology. We might be wiped out by an asteroid impact or a supervolcanic eruption or a nearby supernova. We might simply die out, our brief moment in the cosmos ending without a trace. The choice, to the extent we have one, is ours. The universe won't save us. It won't even notice if we disappear, but we can save ourselves if we choose to. Let me talk about the speed of light, because understanding this cosmic speed limit helps explain why Earth's isolation is so profound. Light travels at about 186,000 miles per second. That's fast enough to circle Earth about 7.5 times in a single second. It's so fast that in everyday life, light appears to travel instantaneously. When you flip a light switch, the room lights up immediately. There's no perceptible delay. But over cosmic distances, even light takes time. Light from our central star takes about 8 minutes and 20 seconds to reach Earth. Light from the moon takes about 1.3 seconds. Light from the nearest star takes over 4 years. Here's something profound about this. When you look at the sky at night, you're looking into the past. The light from each star left that star years or decades or centuries or millennia ago. The farther away something is, the further back in time you're seeing. And here's something even more remarkable. The light we see with our eyes represents only a tiny fraction of the electromagnetic spectrum. Visible light occupies a narrow band between wavelengths of about 400 and 700 nanometers. Below that lies ultraviolet, then X-rays, then gamma rays. Above it lies infrared, then microwaves, then radio waves. The universe looks completely different at different wavelengths. In radio waves, the sky is dominated by the remnants of ancient supernova explosions, pulsars spinning hundreds of times per second, and the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. In X-rays, the sky reveals black holes feeding on infalling matter, neutron stars with intense magnetic fields, and gas heated to millions of degrees in galaxy clusters. Our eyes evolved to see the wavelengths that pass most easily through Earth's atmosphere and that are most useful for survival on our particular planet. We're blind to most of the electromagnetic spectrum. The universe is constantly speaking in frequencies we can't hear, showing us wonders we can't see without special instruments. It took us centuries to develop the technology to see beyond visible light. Each new wavelength we learned to detect opened a new window on the cosmos, revealing phenomena we never knew existed. Who knows what else we're missing? What forms of radiation or information might be passing through us right now, undetected? When you look at the Andromeda Galaxy, you're seeing light that left 2.5 million years ago. Our ancestors were just beginning to use stone tools when that light began its journey. Everything that has happened in human evolution since then, from the development of language to the building of cities to this very moment, has occurred while that light was traveling through space. When the James Webb Space Telescope images galaxies 13 billion light-years away, it's seeing those galaxies as they were 13 billion years ago, less than 1 billion years after the Big Bang. Those galaxies don't look like that anymore. They've been evolving for 13 billion years since that light left them. Some of the stars in those images have long since exploded. Some of those galaxies have merged with others. What we're seeing is history, frozen in light. This means there's a fundamental limit to how much of the universe we can ever know. We can only see objects whose light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old, so we can't see anything beyond a certain distance. The observable universe has a radius of about 46.5 billion light-years, because space has been expanding while light was traveling. But the universe almost certainly extends beyond what we can observe. How far? We don't know. It might be a few times larger than the observable universe. It might be millions of times larger. It might be infinite. If the universe is infinite, then no matter how far we could ever see, there would always be more beyond. The observable universe, immense as it is, would be an infinitesimally minuscule fraction of the whole, and nothing can travel faster than light. This isn't just an engineering limitation that we might overcome with better technology. It's a fundamental law of physics, built into the structure of space-time itself. As objects approach the speed of light, strange things happen. Time slows down, mass increases. The energy required to accelerate further grows without bound. Reaching light speed would require infinite energy, which is impossible. This means that even if we develop incredible technologies, even if we build spacecraft far beyond anything we can currently imagine, we'll still be limited to speeds below light speed. Reaching the nearest star would take years at best, centuries or millennia at worst. Reaching other galaxies would take millions of years. The universe is not just big, it's isolated. The distances between objects are so immense that meaningful contact between distant civilizations might be impossible. We could be surrounded by intelligent life and never know it, because the light from their worlds hasn't reached us yet, or because they're too far away for any signal to ever bridge the gap. Let me tell you about something called the Drake equation, because it helps us think about whether we're alone in the universe. In 1961, astronomer Frank Drake proposed an equation to estimate the number of intelligent civilizations in our galaxy that we might be able to communicate with. The equation multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction of those planets where life actually develops, the fraction where intelligent life evolves, the fraction that developed technology we could detect, and how long such civilizations last on average. The problem is that we don't know most of these values. We have good estimates for some, like the rate of star formation and the fraction of stars with planets. But we have no idea how often life arises on potentially habitable planets, or how often intelligence evolves, or how long technological civilizations survive. Depending on what values you plug in, the Drake equation can give you answers ranging from "we're alone in the galaxy" to "there are millions of civilizations." It's not really an equation that gives us an answer. It's a framework for thinking about the question. Recent discoveries have filled in some of the blanks. We now know that planets are common. Most stars have at least one planet, and many have multiple planets. Some of these planets are in the habitable zones of their stars, where temperatures could allow liquid water to exist. The Kepler Space Telescope, which operated from 2009 to 2018, discovered over 2,700 confirmed exoplanets. Based on Kepler's data, astronomers estimate there could be billions of Earth-sized planets in habitable zones in our galaxy alone. But having a habitable planet doesn't guarantee life. We still don't know how life originates. It might be easy, happening wherever conditions are right. Or it might be incredibly unlikely, requiring a rare combination of circumstances that might have occurred only once in the entire observable universe. And even if simple life is common, intelligent life might be rare. Life existed on Earth for about 3.5 billion years before anything resembling intelligence evolved. During that time, dinosaurs ruled for 160 million years without developing technology. Intelligence might require specific conditions that rarely occur. The Fermi paradox asks why, if intelligent civilizations are common, we haven't detected any sign of them. No radio signals, no evidence of megastructures, no visitors. The universe seems silent and empty. There are many proposed solutions. Maybe intelligent life is extremely rare. Maybe civilizations tend to destroy themselves before they can spread to the stars. Maybe they're out there, but we haven't been looking long enough or in the right ways. Maybe they're deliberately hiding or avoiding contact. Maybe the universe is simply too big and too old for civilizations to find each other. We don't know the answer. But the question matters because it speaks to whether we're alone, whether the universe is teeming with life or nearly empty, whether Earth is ordinary or extraordinary. Let me discuss what makes consciousness so remarkable, because this is ultimately what makes Earth significant despite its modest size. Consciousness is the experience of being aware. Right now, You're experiencing these words. You're aware of your surroundings, your thoughts, your feelings. There's something it's like to be you. This inner experience, this subjective awareness, is consciousness. We don't understand consciousness. It's one of the hardest problems in science and philosophy. How do physical processes in the brain give rise to subjective experience? How do neurons firing produce the sensation of seeing red or feeling joy or wondering about the meaning of life? Some philosophers argue that consciousness can't be explained by physics alone, that there's something fundamentally non-physical about experience. Others argue that consciousness will eventually be explained by neuroscience, that it's an emergent property of sufficiently complex information processing. The debate continues, with no resolution in sight. What we do know is that consciousness exists. You are conscious right now. You are experiencing these words, processing them, thinking about them. Whatever consciousness is, it's real. And as far as we know, consciousness is extremely rare. Most matter in the universe is not conscious. Stars are not conscious. Galaxies are not conscious. The overwhelming majority of the universe consists of unconscious matter and energy, following physical laws without any inner experience. Even on Earth, where life is abundant, consciousness seems limited. Plants are alive but probably not conscious in any meaningful sense. Organisms like jellyfish respond to their environments but likely don't have rich inner experiences. Even among complex animals, the nature and extent of consciousness varies. Human consciousness is particularly remarkable. We're not just aware, we're aware that we're aware. We can think about thinking. We can reflect on our own existence, wonder about our place in the universe, contemplate questions that have no practical bearing on our survival. This reflexive awareness, this ability to step back and consider ourselves from outside, might be unique to humans, or it might be shared by some other species, perhaps dolphins or great apes or elephants. We don't know for certain, because we can't directly access the inner experiences of other creatures. What we do know is that Earth has produced at least one species capable of contemplating the universe. Out of all the matter in the cosmos, some of it has organized itself into beings that can ask questions about existence itself. That's extraordinary. If consciousness is rare in the universe, then Earth is remarkable beyond measure. This modest planet is one of the few places, perhaps the only place, where the universe has become aware of itself. Every conscious experience happening right now, every moment of joy or sorrow, every thought or wonder or love, might be happening only here, on this world. Let me discuss something called the cosmic calendar, a way of visualizing the history of the universe that was popularized by Carl Sagan. If you compress the entire 13.8 billion year history of the universe into a single year, with the Big Bang at midnight on January 1st and the present moment at midnight on December 31st, you can see where different events fall. The first stars form in mid to late January. Our galaxy, the Milky Way, forms around March. But then things slow down dramatically. Nothing particularly notable happens for months and months as stars form and die, as generations of stellar nucleosynthesis gradually enrich the galaxy with heavier elements. Our solar system forms in early September. Earth forms around September 6th. Life appears on Earth in late September, surprisingly quickly once conditions become suitable. But then life remains simple for a very long time. For months on the cosmic calendar, Earth is inhabited only by single-celled organisms. Complex multicellular life doesn't appear until mid-November. Dinosaurs appear on December 13th and go extinct on December 26th. The first humans appear at about 11:59 p.m. on December 31st. All of recorded human history, everything from the invention of writing to the present day, occurs in the last 13 seconds of the year. Think about that. If the history of the universe were a year, human civilization would fit in the last 13 seconds. Everything we think of as human history, every empire, every war, every scientific discovery, every work of art, every human life ever lived, all of it happens in less time than it takes to count to 15. We are incredibly recent arrivals on the cosmic scene. The universe existed for nearly all of its history without us. If the universe were a person, we would have appeared in the last fraction of a heartbeat before midnight. And yet, in those few seconds, we've accomplished remarkable things. We've figured out the age of the universe itself. We've understood the laws that govern matter and energy. We've sent machines to every planet in our solar system. We've detected gravitational waves from colliding black holes billions of light years away. In cosmic terms, we just got here. But we've already begun to understand the cosmos that created us. That's extraordinary. Let me discuss something called the anthropic principle, because it relates to why we find ourselves on a planet like Earth. The anthropic principle notes that the universe appears to be fine-tuned for the existence of life. The fundamental constants of physics, the strength of gravity, the mass of the electron, the charge of the proton, are all precisely what they need to be for atoms to form, for stars to burn, for planets to exist, for chemistry to happen, for life to be possible. If any of these constants were slightly different, the universe would be very different. If gravity were slightly stronger, stars would burn out too quickly. If it was slightly weaker, stars might not form at all. If the electromagnetic force were different, atoms might not be stable, and so on for dozens of fundamental constants. Why is the universe this way? There are several possible explanations. One is that there's only one possible way for the universe to be, that the constants are fixed by some deep principle we haven't discovered yet. In this view, the fine-tuning is an illusion. The universe couldn't have been any other way. Another is that there are many universes, perhaps infinitely many, each with different fundamental constants. Most of these universes don't allow life, but we necessarily find ourselves in one of the rare universes that does, because we couldn't exist in the others. This is the multiverse explanation. Another is that the universe was designed, created by some intelligence, with the intention of producing life. This is the design explanation, which some find appealing and others find unscientific because it can't be tested. We don't know which explanation is correct. But the anthropic principle reminds us that our existence is not guaranteed. The universe didn't have to be this way. The fact that it is, the fact that we exist to ask these questions, is remarkable. Earth is the product of a long chain of cosmic events, each of which had to happen in a particular way for us to be here. The Big Bang had to produce the right conditions. The first stars had to form and explode, enriching space with heavy elements. The right cloud of gas and dust had to collapse to form our solar system. Earth had to form at the right distance from its star, with the right conditions for life. Life had to arise and evolve over billions of years to produce us. Change any link in this chain, and we wouldn't exist. We are here because of a specific sequence of events stretching back nearly 14 billion years. That makes our existence worth protecting, not because we were inevitable, but because we were improbable. Let me tell you about something called the Kardashev scale, because it gives us a way to think about where humanity might be going. In 1964, Soviet astronomer Nikolai Kardashev proposed a way to classify civilizations based on the amount of energy they can harness and use. A Type 1 civilization can harness and use all the energy available on its home planet. This includes geothermal energy, solar energy falling on the planet, and potentially nuclear energy. Earth currently uses about 18 terawatts of power. A Type 1 civilization would use around 170 petawatts, roughly 10,000 times more than we currently use. A Type 2 civilization can harness and use all the energy output of its star. This might involve building enormous structures around the star to capture its energy, like a Dyson sphere or swarm. Our star outputs about 386 yottawatts, roughly 20 billion times more energy than a Type 1 civilization would use. A Type 3 civilization can harness and use all the energy of its entire galaxy. The Milky Way outputs roughly 4 times 10 to the 37th watts. A Type 3 civilization would command energy on scales we can barely imagine. Where does humanity fall on this scale? We're not even Type 1 yet. Carl Sagan estimated that Earth is currently at about Type 0.73 on a logarithmic scale. We're still extracting energy primarily from fossil fuels, ancient sunlight stored in dead organisms. We're only beginning to directly harness nuclear energy, geothermal energy, and current solar energy. If we continue to develop, we might reach Type 1 status in a few hundred years. Type 2 might take thousands or tens of thousands of years. Type 3, if it's even possible, might take millions of years. But there's no guarantee we'll continue to develop. We might plateau, we might collapse, we might destroy ourselves. The Kardashev scale assumes continued growth, which isn't guaranteed. Let me discuss something about the nature of time and energy, because it reveals something profound about Earth's place in the cosmos. Time flows in one direction. The past is fixed and the future is open. We remember yesterday, but not tomorrow. Eggs break, but don't unbreak. This seems obvious, but it's actually one of the deepest mysteries in physics. The fundamental laws of physics are time-symmetric. They work equally well forward and backward. If you watch a video of billiard balls colliding, you can't tell from the physics alone whether the video is playing forward or backward. Both directions are consistent with the laws of motion. And yet, in the real world, time has a direction. Things fall apart. Order becomes disorder. The universe is running down, heading toward a state of maximum entropy, maximum disorder. This is the second law of thermodynamics. Entropy, a measure of disorder, tends to increase over time in closed systems. A neat room becomes messy. Hot coffee cools. Energy spreads out and becomes less useful. But here's what's remarkable. Even as the universe as a whole increases in entropy, local regions can temporarily decrease in entropy. Life does this. Living organisms maintain their internal order by taking in energy and expelling waste. They're islands of low entropy in a universe of increasing disorder. Earth is one such island. Solar energy streams in. Life uses that energy to build complex structures, to grow and reproduce, to maintain order against the tide of entropy. Eventually, the waste heat radiates out into space, carrying entropy away. This makes Earth special. In a universe that's running down, that's heading toward disorder and heat death, our planet is a temporary refuge of complexity and order. Life here is fighting against the cosmic trend, building structures and maintaining organization against the fundamental direction of time. It won't last forever. Eventually, our star will die. Eventually, all stars will die. Eventually, the universe will reach a state of maximum entropy, what physicists call heat death, a cold, dark, uniform void with no structure and no possibility of change. But for now, for a brief cosmic moment, Earth exists, life exists, consciousness exists. We are temporary patterns of order in an increasingly disordered universe, and that makes our existence remarkable. What's interesting is that we've never detected evidence of Type 2 or Type 3 civilizations. A Type 2 civilization building structures around its star would be visible. A Type 3 civilization harnessing galactic energy would be extremely visible. And yet, when we look out at the universe, we don't see any clear signs of such civilizations. This is another aspect of the Fermi paradox. If advanced civilizations are possible, and if they tend to expand and harness more energy over time, why don't we see any evidence of them? The universe should be filled with Type 2 and Type 3 civilizations, but it appears empty. Maybe advanced civilizations don't expand indefinitely. Maybe they reach some limit and stop. Maybe they destroy themselves before they can become Type 2. Maybe they exist, but we can't recognize them. Or maybe we're among the first, arising early in cosmic history when the universe is still young. We don't know. But the Kardashev scale gives us a framework for thinking about humanity's potential future, assuming we survive long enough to have one. Let me share something about the nature of scientific knowledge itself, because this relates to how we understand Earth's place in the cosmos. Everything I've told you tonight is based on science. The size of Earth, the distance to the stars, the age of the universe, all of these come from careful observation, measurement, and analysis. Science is our best method for understanding the natural world. But scientific knowledge is provisional. It's based on evidence. And as evidence changes, knowledge changes. What we think we know today might be revised or even overturned by future discoveries. 100 years ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. 50 years ago, we didn't know planets orbited other stars. We suspected they might, but we had no evidence. 20 years ago, we didn't know dark energy existed. We thought the universe's expansion was slowing down. Each of these discoveries fundamentally changed our understanding of the cosmos. Each showed us that the universe was different from, and usually larger than, we had thought. What will we discover in the next 100 years? We can't know. But if history is any guide, we'll discover that the universe is stranger and more complex than we currently imagine. Our picture of reality is incomplete, and it always will be. This doesn't mean scientific knowledge is unreliable. Quite the opposite. Science is reliable precisely because it's willing to change in response to evidence. Unlike belief systems that claim certainty, science acknowledges uncertainty and revises itself as needed. What I've told you tonight represents our current best understanding. The measurements are precise. The calculations are sound. But there's always more to learn. Always deeper questions to ask. Always new discoveries waiting to be made. Consider what we still don't know. We don't know what dark matter is, even though it makes up about 27% of the universe's mass energy content. We don't know what dark energy is, even though it makes up about 68%. Together, the stuff we don't understand constitutes 95% of the universe. The ordinary matter we're made of, the atoms and molecules we can see and touch, represents only about 5% of everything that exists. We don't know how life began. We don't know if we're alone in the universe. We don't know if consciousness is unique to biological brains or could arise in other substrates. We don't know what happened before the Big Bang, or if that question even makes sense. We don't know if the universe is finite or infinite, if there are other universes, if time and space are fundamental or emergent. These aren't failures of science, they're frontiers. They're the places where knowledge ends and mystery begins. And pushing those frontiers outward, one discovery at a time, is one of the noblest things humans do. Think about what it means that we can understand any of this. Human brains evolved on the African savanna to help us find food, avoid predators, and navigate social relationships. We developed to understand distances we could walk in a day, quantities we could count on our fingers, time spans measured in seasons and generations. Nothing in our evolutionary history prepared us for light years, trillions of galaxies, or billions of years. These scales are so far beyond our daily experience that our brains can't really comprehend them intuitively. We can write down the numbers, do the calculations, and understand them intellectually. But we can't feel what a light year means the way we can feel the distance across a room. And yet, somehow, we figured it out. Using nothing but our pattern-recognizing primate brains, some clever tools, and the accumulated knowledge of generations, we've measured the universe. We've determined that our star is 93 million miles away, that the nearest star is 4 light years away, that our galaxy is 100,000 light years across, and that the observable universe contains trillions of galaxies. This is extraordinary. It might be the most remarkable thing about humans. We're modest creatures on a modest planet, but we've learned to think big. We've learned to see beyond our immediate surroundings and comprehend a universe far vaster than anything our ancestors could have imagined. Consider also what we've learned about our origins. Every atom in your body was forged in the heart of a star. The hydrogen atoms have been around since shortly after the Big Bang, about 13.8 billion years ago. The heavier elements, the carbon in your cells, the calcium in your bones, the iron in your blood, were all created inside stars that exploded billions of years ago, scattering their contents across space. Eventually, some of that star debris gathered together under gravity to form our star and its surrounding disk of gas and dust. From that disk, Earth formed. From the complex chemistry on Earth's surface, life emerged. And from billions of years of evolution, we appeared. You are literally made of stardust. The atoms in your body have been on a journey lasting billions of years, through stellar cores and supernova explosions and interstellar clouds and the formation of planets and the evolution of life. Every atom has a history older than Earth itself. This connects us to the universe in a profound way. We're not separate from the cosmos, looking at it from outside. We're part of it. We're made of it. When you look up at the stars, you're looking at the places where the atoms in your body were made. Think about the improbability of your existence. The exact arrangement of atoms that makes you who you are required a specific sequence of events stretching back billions of years. Different initial conditions after the Big Bang would have produced a different universe. A slightly different supernova would have scattered different elements. A slightly different orbit for Earth would have made it too hot or too cold. A slightly different asteroid impact might have wiped out our ancestors instead of the dinosaurs. You exist because of a chain of events so long and so specific that the odds against it are astronomical. And yet, here you are, breathing, thinking, reading these words. Improbable doesn't begin to describe it. Some people find this perspective humbling to the point of being depressing. If we're so compact in cosmic terms, so improbable, so cosmically minor, What's the point? Why does anything matter? But I see it differently. The fact that we exist at all, against such tremendous odds, makes existence worth appreciating. The fact that we can understand our place in the universe, despite having brains designed for African savannas, makes that understanding a triumph. The fact that we're modest in scale makes our achievements grand by comparison. A bacterium doesn't know it's compact in scale. A rock doesn't wonder about its place in the cosmos. But we do. We can look up at the night sky and understand, at least partially, what we're seeing. We can measure distances to galaxies billions of light years away. We can trace our origins back to the Big Bang itself. That's not nothing. That's remarkable. That might be the most remarkable thing in the universe as far as we know. The philosopher Blaise Pascal, writing in the 17th century, contemplated the immensity of space. He wrote that the eternal silence of these infinite spaces frightened him. Pascal saw the cosmos as terrifying precisely because it is so immense and we are so modest in comparison. But there's another way to see it. The cosmos is immense, yes, but it's also knowable. We can measure the distances to galaxies. We can understand the physics that governs stars. We can trace our origins back to the Big Bang itself. The universe may be silent, but it's not opaque. It speaks to us through light and mathematics, and we have learned to listen. Carl Sagan offered a different perspective. He wrote that we are a way for the universe to know itself. In this view, our modest scale is beside the point. What matters is that we exist at all, that matter has organized itself into beings capable of contemplation and wonder. Both perspectives are valid. We are modest in scale and vulnerable, adrift in an immense and indifferent cosmos. But we are also aware and capable of understanding, perhaps the universe's only way of knowing itself in this region of space. We've explored Earth's size from many angles. We've compared it to the moon, to the planets, to our star, to other stars, to galaxies, and to the observable universe itself. At every scale, Earth becomes tinier and tinier until it essentially vanishes from view. If you made a scale model of the observable universe the size of Earth, our entire galaxy would be smaller than an atom, and Earth would be far, far tinier than that. At cosmic scales, Earth doesn't just become modest. It approaches non-existence. But we've also explored what makes Earth special. Its thin atmosphere, its liquid water, its magnetic field, its plate tectonics, its large moon. All these factors combine to create a world uniquely suited for life. And life has flourished here for nearly 4 billion years, producing everything from bacteria to blue whales to beings capable of pondering their place in the cosmos. Earth is modest in scale, yes, cosmically minor by any measure of size or position. We're one planet orbiting one star among hundreds of billions of stars in one galaxy among trillions of galaxies. The probability of randomly selecting Earth from everything in the observable universe rounds to 0. And yet Earth is extraordinary. As far as we know, it's the only place where life exists, the only place where consciousness has arisen, the only place where beings can look up at the stars and wonder. In all the immense cosmos, Earth might be unique, a tiny oasis of life and awareness in an otherwise dead and silent universe. This perspective should change how we see ourselves and our world. The conflicts that divide us, the borders we fight over, the resources we compete for, all of it happens on a world that's practically invisible from even nearby stars. From a cosmic perspective, we're all neighbors, all residents of the same world, all made of the same atoms, all sharing the same thin layer of atmosphere. But this perspective shouldn't make us feel insignificant, because significance isn't about size. A mother's love for her child isn't less meaningful because it happens on a modest planet. A beautiful sunset isn't less beautiful because Earth is tiny. The joy and sorrow, the triumphs and tragedies, the meaning we find in our lives, none of that depends on how big our planet is. What the cosmic perspective gives us is context. It reminds us that the conditions allowing life are delicate, that we should take care of the only home we've ever known. It reminds us that we're all in this together, 8 billion people sharing one world. It reminds us that what happens here matters, perhaps more than we realize, because there might be nowhere else like this in all the universe. The next time you look up at the night sky, remember what you've learned. The stars you see are distant suns, many far larger than ours. The faint smudge of the Milky Way is our galaxy, containing hundreds of billions of stars. Beyond it lie trillions more galaxies, each containing billions or trillions of stars. Consider what our ancestors saw when they looked up. They saw the same stars we see, the same patterns, the same Milky Way stretching across the darkness. But they had no idea what they were looking at. They thought the stars were holes in a celestial dome, or lights hung by gods, or the campfires of ancestors in the afterlife. They had no concept of how far away those lights were, or how large, or what they were made of. Over thousands of years, we figured it out. We measured the distances. We discovered that stars are suns like our own, that they're made of hydrogen and helium, that they're born in nebulae and die in spectacular explosions. We learned that the Milky Way is a galaxy, one of trillions, and that our star is just one of hundreds of billions within it. This knowledge came slowly, through countless observations, calculations, arguments, and discoveries. Each generation built on the work of those before. The cumulative achievement of astronomy, from ancient stargazers to modern space telescopes, is one of humanity's greatest intellectual accomplishments. And we're not done. Every year brings new discoveries, new planets around other stars, new galaxies at the edge of the observable universe, new mysteries that deepen our questions even as they answer old ones. The universe keeps revealing itself, and we keep learning. The ancient Greeks looked up and saw stories written in the stars, heroes and monsters frozen in constellations. We look up and see thermonuclear furnaces fusing hydrogen into helium, planets orbiting in habitable zones, galaxies colliding in slow motion over hundreds of millions of years. Both visions have their beauty. But the scientific vision is true, as far as we can tell, and that truth adds a depth of wonder that myth alone cannot provide. And here we are, on a rocky planet, looking up and wondering. We are the universe becoming aware of itself. We are stardust that has learned to contemplate the stars. That's remarkable. No matter how modest our planet is, Earth is tiny. But Earth is also home, and in all the immense cosmos, that might be the most extraordinary thing of all. Thank you for joining me on this journey through the cosmos. If this exploration gave you a new perspective on our world, please consider liking and subscribing. Your support helps me continue making these deep dives into space and our place in it. The universe is enormous. Earth is modest in scale. But significance isn't measured in size. It's measured in awareness, in understanding, in the ability to wonder. And by that measure, you are remarkable. You are literally made of atoms forged in stars, existing against astronomical odds, capable of comprehending a universe billions of light years across. Remember that modesty in scale and significance aren't the same thing. The cosmos doesn't care about us, but we can care about each other. We can care about truth and beauty and meaning. We can make our brief moment on this world count for something. We're here, on this tiny world, looking up at the stars. Let's make it mean something. Sleep well tonight, knowing you're part of something vast and beautiful. The universe is enormous. Earth is modest in scale. But what happens here matters. You matter. And this delicate, extraordinary world we call home is worth protecting. Good night and clear skies.